Before the universe existed, there was no space, no time, no matter, no light, and somehow, out of that absolute void, 13.8 billion years of stars, galaxies, planets, and you came screaming into existence. Scientists call it the Big Bang. But that name is almost laughably inadequate for what actually happened, because this wasn't an explosion inside space, it was the explosion of space itself. And the most disturbing part? Physics suggests it may have required nothing at all to get started. Here is what we actually know about how everything came from nothing. To understand the beginning, you first have to understand what physicists mean when they say the word nothing. Because the nothing of everyday language, an empty room, a blank canvas, outer space, is not nothing in the physics sense. Not even close. True physical nothingness would mean the complete absence of space, time, matter, energy, and even the laws that govern them. That kind of nothing may be philosophically impossible to fully imagine, but in the moments before the Big Bang, something resembling it may have been the only thing that existed, or wasn't. Quantum mechanics, the rulebook for the universe at its smallest scales, tells us that nothing is inherently unstable. Genuine emptiness cannot hold still. Even in a perfect vacuum, a region stripped of every particle, every photon, every scrap of matter, the laws of quantum physics demand that energy fluctuates constantly. Space itself is not quiet. It seethes. It churns with what physicists call the quantum vacuum, a roiling sea of activity so fundamental that it has no off switch. And here is the thing about the quantum vacuum. It is measurable. It is real. In the 1940s, physicists discovered something called the Casimir effect. Place two uncharged metal plates close together in a vacuum, and they will push toward each other. No magnets, no charge, nothing touching them. The only explanation is the pressure of virtual particles, particles that blink in and out of existence so briefly that they technically never violate the laws of physics, but are real enough to physically move metal. Werner Heisenberg figured out why this happens. His uncertainty principle, one of the most unsettling ideas in all of science, says that the more precisely you measure the energy of a system at a given moment, the less precisely you can know when you measured it. This creates a loophole in the universe's accounting. Energy can be borrowed from nothing, so long as it is paid back fast enough, short-term, spontaneous, unannounced. That loophole is where everything begins. At the very smallest scales, a scale called the Planck length, roughly 10 to the negative 35 meters, a distance so inconceivably tiny that putting it in context is almost pointless. Space itself stops behaving like smooth, continuous fabric. It becomes grainy, chaotic. John Wheeler, one of the great theoretical physicists of the 20th century, called it quantum foam. At that scale, space-time does not lie flat. It bubbles. It writhes. Tiny regions of space pop into existence and collapse back out of it in fractions of a nanosecond. Space and time themselves become uncertain. Wheeler described it in 1955, and the idea has never been fully shaken. In those quantum foam bubbles, the conditions for a universe might arise spontaneously, a fluctuation not just of particles, but of space-time itself. Physicist Edward Tryon was the first to formally suggest, in 1973, that the universe might be one of these fluctuations, a quantum bubble that, instead of collapsing, kept growing. He proposed that the total energy of the universe could be exactly zero. The positive energy locked inside all matter is perfectly cancelled out by the negative energy of gravity pulling everything together. Net cost, nothing. A universe that required no energy to create because it contains no net energy at all. That idea sat on the fringe for years. Then Alan Guth walked in and changed everything. In 1979, Guth was a young physicist trying to solve a nagging problem. If the Big Bang just exploded outward in all directions, the universe should be lumpy, uneven, wildly different from one region to the next. Instead, no matter which direction we look, the universe is almost perfectly uniform. Galaxies spread evenly, the temperature the same everywhere. Two regions of the universe billions of light years apart, regions that could never have been in contact with each other, somehow have nearly identical properties. How? Guth's answer was cosmic inflation, a period in the first 10 to the negative 32 seconds, a sliver of time that makes a nanosecond look like an eternity, when the universe expanded faster than the speed of light. Not matter moving through space, space itself expanding. The universe grew by a factor of at least 10 to the 30 in a fraction of a heartbeat. Everything that now makes up the observable universe, 93 billion light-years of galaxies, clusters, and voids, was compressed into a region smaller than a single proton before inflation began. And here is the part that connects back to nothing. Those tiny microscopic quantum fluctuations in the early universe were stretched during inflation from subatomic scales to cosmic scales. The random, chaotic noise of the quantum vacuum became the blueprint for the entire large-scale structure of reality. The galaxies you see in deep-field images from the James Webb Space Telescope, those vast glowing islands of billions of stars, are where they are because of quantum uncertainty that existed in the first fraction of a second of time. Nothing left fingerprints all over everything. The first second of the universe's existence was a wall of fire unlike anything that has existed since. Temperature: 10 to the 32 degrees Kelvin. Every cubic centimeter of space packed with energy so dense, so violent that no particle could hold together. There were no atoms, no protons, no neutrons, just an undifferentiated plasma of quarks, gluons, and radiation screaming through space in every direction. At 1 microsecond, 1/1,000,000th of a second, the temperature dropped just enough for quarks to bind. 3 at a time, they snapped together into protons and neutrons. For every billion antiparticles created, there were 1,000,000,001 particles. One extra particle for every billion. That tiny asymmetry, something physicists still cannot fully explain, is the reason the universe contains matter at all. Everything you have ever seen, touched, or loved is the remainder of a near-perfect annihilation. 1 second in, the temperature had fallen to 10 billion degrees Kelvin. Protons and neutrons existed, but nothing more complex. The universe was still too hot for anything to stick. Then, between roughly 3 minutes and 20 minutes after the Big Bang, something remarkable happened. The temperature dropped into a narrow window where protons and neutrons could fuse. For those 17 minutes, the universe was a nuclear furnace. Hydrogen fused into deuterium, deuterium into helium. Trace amounts of lithium formed. Then the window slammed shut. The universe had expanded and cooled past the point where fusion was possible. Nucleosynthesis was over. The elemental inventory of the cosmos was set. Approximately 75% hydrogen, 25% helium, and traces of lighter elements. That ratio still holds today, but the universe was still dark, still opaque. For the next 380,000 years, light could not travel. Every photon emitted was immediately absorbed, scattered, bouncing endlessly through a fog of free electrons and nuclei. The universe was a plasma, glowing from within, but sealed off from itself. An enormous roiling cloud too hot for electrons to settle into orbit around any nucleus. Then, at 380,000 years, the temperature finally dropped below 3,000 degrees Kelvin. Electrons slowed. Nuclei captured them. Atoms formed for the first time, and the fog lifted. In an instant, cosmologically speaking, the universe became transparent. All that trapped light, 380,000 years of it, flooded outward in every direction simultaneously. That light is still traveling, right now. It surrounds you. Physicists detected it in 1964, two radio engineers named Arno Penzias and Robert Wilson, who noticed an unexplained hiss in their antenna, a faint glow coming from every direction in equal measure. They thought it was bird droppings fouling their equipment. It was the echo of creation. They won the Nobel Prize in Physics in 1978 for the discovery of what we now call the cosmic microwave background radiation. That radiation today has a temperature of 2.73 degrees Kelvin, just barely above absolute zero, stretched cold by 13.8 billion years of cosmic expansion. But in its tiny variations, its 1 part in 100,000 fluctuations from one patch of sky to another, you can read the quantum fingerprints of the very beginning. Those fluctuations match exactly with the quantum noise that inflation stretched to cosmic scale. A map of the ancient quantum vacuum, pressed into the oldest light in the universe. Now pause on that for a moment. The entire structure of the observable universe, every galaxy, every cluster, every supervoid stretching hundreds of millions of light-years across, traces back to microscopic quantum uncertainty in the first instant of time. Not random chance, not design. Quantum mechanics, operating in the most extreme environment imaginable, leaving an imprint we can still read today. There is one more layer to this that most people never confront. We said the universe is 13.8 billion years old, but what we mean is the observable universe, the part we can see. Light has had 13.8 billion years old, but what we mean is the observable universe. So that is the horizon of our vision, but the universe almost certainly extends far beyond that horizon, possibly infinitely. And the CMB data suggests our observable portion, 93 billion light-years across, is just one tiny patch of a vastly larger whole. Some physicists go further. Alan Guth himself, along with André Linde and others, developed what is called eternal inflation, the idea that inflation never truly stopped everywhere at once. Instead, bubbles of non-inflating space pinch off as separate universes, while the space between them keeps inflating forever. In this model, our Big Bang was not the beginning of everything. It was the birth of one bubble in an infinite sea of bubbles, a multiverse where the laws of physics may differ from one region to the next. Our universe could be one quantum fluctuation among an infinite number of others, each with different constants, different forces, different possibilities for life. Most of those universes would be empty, sterile, hostile to any complexity. We live in the one that got it right, or the one that got it right enough. And then there is the deepest question of all, the one Lawrence Krauss pressed hard against in his landmark work on the quantum origins of the universe. Even if quantum mechanics can create space, time, matter, and energy from the quantum vacuum, where did the quantum vacuum come from? Where did the laws of physics themselves come from? That is a question science has not yet answered. Maybe it cannot. Maybe the question itself breaks down at that boundary, the same way asking what is north of the North Pole breaks down as a question. Or maybe, and this is the possibility that genuinely should keep you up at night, the answer is that there is no reason. There is no cause. The laws, the vacuum, the fluctuation, the inflation, the atoms, the stars, the planets, and us, all of it emerged from a structure so fundamental that asking what preceded it has no meaning. Not because we haven't found the answer yet, but because there is no answer to find. Consider what that means. Every mountain, every ocean, every city, every song, every person who has ever lived or loved or grieved, all of it built on a foundation of pure, lawless, uncaused quantum chance. The universe was not born from something. It was not built by anyone. It erupted from an instability so profound that even nothing could not hold still. And every atom in your body was forged in the aftermath. Here's what I want you to sit with. We know with extraordinary precision how the universe evolved in its first seconds. We can calculate the ratio of hydrogen to helium. We can trace quantum fluctuations to galaxy clusters. We can read 380,000-year-old light. But the moment before it all began, the actual instant of origin, remains just out of reach. Every time physics gets close, the math breaks down. So what do you think was there? Before the quantum vacuum? Before the laws? Before space and time themselves? Drop that question in the comments. I want to see what you think nothing actually is. If this cracked your brain open a little, hit the like button and share it with someone who needs their mind broken today. Make sure you're subscribed because next time we're going somewhere even stranger, the place where time itself may stop, the physics of a black hole's final moment. You do not want to miss that one.